yeah, primitives are very, very powerful. Yeah, our code is available on GitHub. So you can see the link there, yeah, we'll talk about more about that in a second. Regarding myself, I founded a company and I'm also the CTO. And before Sneller, I was actually CTO at a company called Minio, which some of you might know as sort of an open source S3 compatible object storage, also developed in Golang. Yeah, I also have Phil Hover on the call, and yeah, Phil has been very instrumental in building Sneller. So yeah, he's basically the chief software architect, and he will do kind of the lowest level part of the this talk. But let me move on to sort of give a high level picture of Sneller. You know, it's actually reasonably simple in the sense that Sneller is a fully stateless architecture. So fundamentally, you know, the Sneller is, you know, a bunch of compute in the cloud, meaning a bunch of cores, bunch of memory, and fast networking. There's no need to use any local storage like SSD or NVMe. And fundamentally, all the data lives in object storage, effectively on AWS. Obviously, that is S3, but yeah, it can also work with other cloud solutions. And what we are seeing in practice is that you know, if you have to manage huge quantities of data, whether they're coming from, you know, security applications or observability applications or IoT data sensors, and so, you know, all sorts of operations, whether they're, you know, DevOps or MLOps or even AIOps, we see the data being aggregated at scale into object storage, and also yeah, that happening a lot basically with or as JSON data. And this means fundamentally that you know, JSON is obviously super flexible, so that ideally you would want to work in a schemaless fashion and not be forced into some kind of a rigid a schema. So fundamentally, you know, if there's terabytes and terabytes, or even tens or hundreds of terabytes of JSON data and object storage, our engine allows yeah, to query that data at speed with basically sort of SQL. Yeah, that's essentially sort of our architecture. So there's not a lot of moving parts. And you know, I have some further details in the rest of the presentation. But again, sort of our you know, Sneller you know, servers or cloud solution is just a bunch of compute, a lot of cores, some RAM, and fast networking, and that allows you to deal with huge quantities at scale. I talk about the fact that really sort of the source of the data that we see is fundamentally JSON. But unlike some other solutions, you know, we basically standardize on SQL, and actually sort of a kind of a superset of SQL that's called Particle, which is sort of an Amazon or partially an Amazon extension to SQL. But what this allows you to do is to, you know, work with JSON data almost in a JQ query style manner. So, for instance, and I'll show this live later in a demo as well. But some of the data that we've been working with is, for instance, the GitHub archive data, which has billions and billions of records and is very rich data. And let me zoom in a little bit. But for instance, you will notice here's a simple SQL statement that you can do. So a distinct repo.name from basically a bunch of GitHub archive data. and then you can simply do a where repo name with a case insensitive and yeah, that will, well, usually that's pretty standard SQL, with the exception that this part is effectively schema on read. So evaluated at runtime, and SQL being SQL, there's stuff to do, sort of group bys and order bys and stuff like that. What we see kind of more and more is that when people aggregate JSON at scale, you even see sort of free-form sort of payload. So actually, the GitHub archive data, which is basically all the events on GitHub, sort of has a custom payload kind of attribute, which depending on the type of the event, and GitHub has something like 20 events or so, basically has a custom format. So for instance, here we can run a query where we sort of drill down in the payload.pull_request.created_at in order to dynamically kind of traverse the architecture, also depending on sort of the type of the event. And then we support more typical SQL constructs like a time bucket. So basically, you can say aggregate everything on a per day basis if you group by on that. And last but not least, kind of a nice feature. Fundamentally, the output that we generate is also JSON, so you're not getting back a CSV style response as you typically get from a SQL engine. You're basically getting sort of JSON data back out as well. So that means you can even sort of combine multiple queries into a single query, and then you can sort of get sort of sub-objects back. But yeah, that's just a very high level sort of introduction to kind of the sneller query engine. But let me move on to kind of perhaps sort of the most fundamental aspect of our technology. And that actually has to do with the latest generation of SIMD techniques. So on the Intel side, this is called AVX-512, and actually ARM has a pretty similar technology that's called SVE, Scalable Vector Extensions. And while kind of the assembly syntaxes are different, the principles are essentially the same. But if you look back at sort of the previous generations of SIMD architectures that there have been, then obviously AVX-512 is the latest, which has been introduced in sort of 2018 or so, when the first Skylake servers became available. Before that, you had AVX2. Before that, even you had AVX and even SSE. And while all these technologies allow you to do operations in parallel on fundamentally larger words, and typically, that has doubled every generation. So AVX2 has been 256, and AVX-512 is obviously 512. Intel added pretty fundamental, kind of masking capability as part of launching AVX-512. And that means that you can now start to think of essentially a single core as sort of having 16 lanes of execution, where every lane in this case can be 32 bits. The only caveat is, because it's a SIMD architecture, you're not able to run different instructions for different lanes. But what you can do is using mask registers to basically enable certain operations on certain lanes and not have them take effect on other lanes. And in my next slide, I'll have some more details on that. But fundamentally, for us, one core is sort of 16 lanes of execution. So almost, you can think of it as sort of having 16 subcores that we can drive. In turn, that means if you have an 18-core server, for us it's basically 288 parallel lines of execution. And again, if you scale that across servers, if you have 10 servers, each 18 cores, it's basically 3,000 lines of execution power. And again, some of the newer concepts that have been introduced with AVX-512 is this masking or per lane predication. There's also sort of gather, load, and scatter store capabilities. So you can fetch, basically you can dereference 16 pointers sort of in a single instruction and fetch data from different parts in the memory. But let me give a little bit of more detailed example. So obviously, there's many instructions in the AVX-512 instruction set, but it's actually much more like RISC-like than sort of the general x86 sort of architecture. And the registers themselves, they're called Z registers, and every Z register is 512 bits wide. And you actually have 32 of those available. So literally there's like 2 kilobytes of sort of register space per core. And then also there are the mask registers, which are sort of the K registers, and you have basically 8 of those or 7 of those available. And what you see here, let me zoom in a little bit. So this is basically sort of an add instruction, and you have to read this from left to right. So fundamentally, you're adding here from the register 12 with register 7, and it also ends up in register 7. But with this important addition, and this is the K register, so the K register determines on which lane this instruction is actually going to happen. And you can see there's the reason that there's a third D to that instruction is not an error, because this D actually denotes in how many lanes you are now working with this instruction. So the D means that you're operating across 16 lanes, and out of the 512 bits, every lane essentially is 32 bits. But you can also just as easily operate across 8 lanes where every lane is 64 bits, or you can even go down to word or literally a sort of byte lane. So if this instruction word was not a VP at D, but a VP at B, then it would actually take this K register 64 bits wide. So if you operate at the byte level, literally for every byte, you can control whether the operation takes effect or does not take effect. So that is pretty powerful. And to basically take advantage of this, here's a pretty simple example. So in case you would want to either add 2 to a variable in case it's smaller than 3, or maybe subtract 1 if that is not the case. In your traditional sort of assembly language, scalar assembly language, this basically would become sort of jumps. So here you do your compare. If the condition is not false, you kind of jump across the addition with 2. And if you've done that, you jump across the whole sort of if statement. And in case you you skip this or you jump over this guy, you execute sort of this instruction. So that's kind of the simple way essentially a compiler would do that for you. However, with AVX-512, you can parallelize or run this operation in parallel, but you sort of have to do that in what's called a branchless manner. So instead of jumping around, which really, if you work in parallel, you cannot do, you sort of get the same effect by using these mask registers. So what you see here is the first instruction is basically the if clause of the comparison, which results in a mask register, and this mask register, basically for every lane that you are working on will determine whether this condition is valid or not. And then we compute the inverse of the mask instruction in the second assembly instruction, and then we simply do both the add as well as the subtract instruction here, but fundamentally with either the true condition of the sort of if statement or the inverse of the if statement. And what this will do is that, again, depending on the state of K1, the respective lane of ZMN or register 0 will get the result of X incremented by 2, or in case K1 would not be active for that lane, then K2 would become active, and so the inverse of the lanes, if you will, receive the result of the sort of second subtract instruction. So as you can see, there's no jumps in here, but fundamentally you steer your control by using these mask registers, and using these mask registers is really very powerful, and I would say that's pretty much at the heart of sort of what we do. So if you look at, and again, our code is on GitHub, as we sort of operate on the data, fundamentally we're always working sort of on 16 lanes in parallel. So simply speaking, we're sort of processing 16 lanes of records of JSON in parallel on a single core. However, obviously that means if a certain row doesn't meet a certain condition, we kind of turn the bit in the mask register for that particular row kind of off, but that's perfectly fine because that's what we can do. So that's pretty much the introduction that I wanted to give thus far. Are there any questions so far? Maybe before I hand it over to Phil.
We do have a question in the chat. The question is there a extrapolation of the mask to allow more than 2 arms? For example, mask operations.
Yeah, there are 8 mask registers. So if you and you can load and store into them as well. So practically speaking, there's an unlimited number. But yeah, you can have there's an unlimited number of mask registers per operation. There's only one. Only one mask argument that you can typically apply, but you could store 8 simultaneous predicates in registers at once.
Correct.
Another quick question, if that's all right.
Sure.
It looks like you can do a lot of SIMD stuff with ARM, and ARM looks like it's being supported more and more in the cloud. Have you looked into whether or not you can do stuff like this, I guess, specifically for your database using ARM v9 and SVE2?
Yes, that's the short answer.
Yeah.
Yeah. So that I'm actually going to cover that shortly, but the short answer is yes, and I'll talk about how and what presently, we don't have that, and it's mostly a function of manpower.
Okay. When you get to it, I've got another question for you, so I look forward to that. Thanks.
Okay.
Okay. So please take it away.
Sure. So I'm going to try to give you guys a super high-level overview of how we go from a SQL query as a string to something that's actually executable as AVX-512 assembly, because there's a lot that has to happen in between a SQL query and the machine code to make that actually workable. So I'm going to go through this really trivial example here, which is the sum of y from a table where x less than 3. So obviously the first thing you do here is you parse the query into an AST. And then the second thing you do, which is much less trivial, is to convert the AST into a query plan. And I'm not going to spend a whole lot of time on that because that's a whole nother hour-long talk. But the short version is we decompose this SQL query into what we call physical operators. And we connect those, and I have them connected by arrows here. But we build a directed graph of data flow from one operation to another. So you can think of it like a shell pipeline where you're doing one program that's sending data to another one and another one. This query is simple enough. You can represent it as a simple sequence of operations. In practice, it's a directed graph of operations. So you can get a big hairy mess of operations. And each of these arrows actually can go over machines. So it may not even be a local function call. It may be sending the data over a socket because we want to be able to perform these queries on 100 machines at once, for example. Frank, could you go to the next slide?
Yeah. Sure. Yeah, there we go.
Cool. So I'm just going to go through the where x less than 3 part here because that's the simplest example that we can use. So where clauses are decomposed into typically a filter operator, which does pretty much what you'd think it would do. In this case, it's going to evaluate the expression after where, and it's going to remove all the rows for which the expression does not evaluate to true. That's an important distinction from is the expression, does it evaluate to false? Because that's not actually the question. The SQL standard, for example, if you get null in this place, that's still false from the perspective of where. So we're looking for true. This right here is actually the Go doc output if you want to construct a filter from the VM package. All it takes is the AST of the expression, and then what we call a query sync, which is essentially the pipe to the next operation. That's going to take the result from the filter and do something else. And I also have the struct literal representation of what the AST for x less than 3. If you've worked on a compiler or a parser before, it should look kind of familiar. We have a comparison AST node. There's a less on the left side of it is what we call a path expression x, and then on the right side is a literal integer 3. Can I get the next slide?
Yep.
So one of the most difficult things that we do in the VM is convert the expression into an SSA intermediate representation and optimize it. And this is where most of the optimizations actually happen as far as common sub-expression elimination and certain kinds of constant folding and other things. And we use a kind of a weird SSA IR in 2 respects. One is that we don't have any control flow. We use only predicated execution. And you can kind of imagine why we only use predicated execution. And the second thing that's weird about it is that every operation can return more than one value. Most operations accept and return a predicate. So in this example here, we've only got 4 instructions for x less than 3. The first instruction simply represents the initial state of the program, which is the record and true. So K0 is going to represent the true predicate. B0 is going to represent the base of the current structure. The find sim operation that follows it just searches for x with K0 as the mask, so true. So it searches for x unconditionally and then returns V1, so a value, a boxed value, any value. And then K1, the predicate, is V1 actually valid. The next operation, to float, converts the boxed value that the first operation found into a floating point number. And it only does anything with that number if K1 is set. So only if the value was found, convert it to a float. So that's F2, and then K2 is the value was actually a floating point number. Because at no point in this program can we actually assume that X really exists or X is a floating point number, because we're dealing with JSON data. So from one row to the next, X could be non-existent or null or a string or a substructure. And then the final operation here performs, the way to read this would be compare less than immediate float So compare the float f2, if k2 is set against the immediate value 3, return the result as k3 as a predicate, and then the program returns k3, and that represents, did this expression evaluate to true for one row. Note that there's no explicit vectorization here, right? It's just predicated execution. So we're agnostic to the lane layout or anything like that. The model in the SSA is that this program is applied to all the lanes effectively in any order. We don't care about the lane width in the implementation. And so this is where the SVE aspect comes in. We're not stuck with using 16 lanes and 32-bit offsets or anything like that. This high-level representation is sort of portable to other predicated, other vector architectures that support predicated execution. And even those that don't, although with considerably more effort. So I don't think we'll ever attempt that. I see I've got a question in the chat here. String comparison. Yes, we can do string comparison in SIMD. It's a pain, but you can do a gather load from all the string bases and do, basically a 4-byte comparison at a time per lane. We've got a lot of opcodes. Actually, so Frank, if you want to go to the next slide.
Right.
We've got, as I said earlier, I think over 280 opcodes, and these implement things up to and including like Mercator projection for doing geohashing. We have regular expression evaluation. So some of these, the implementation of these opcodes can be hundreds of instructions, and they're all written by hand. So it's a considerable amount of effort to implement them. But the bytecode representation maps more or less one-to-one with the SSA that you saw in terms of the actual instructions themselves. Really the only thing that has to happen to make that representation executable is to serialize, first schedule the instructions in an order that's actually valid to execute. So the SSA is just a data flow graph. So you need to lay it out in some way that's executable. And then additionally, you need to serialize the instructions themselves. And in the next slide, you'll see how those are laid out along with any immediates that are passed to the operations. So it's just a big hunk of bytes that's self-executing in a sense. Another thing that happens at this stage is that we insert stack operations. There's only one, what we call a virtual register assigned for each type that we deal with. And so if you're dealing with multiple types across different instructions, you have to save and load from a virtual stack, which turn into real load and store instructions. And those virtual registers always map to physical registers. So there is a very sort of rudimentary register allocation that's happening. So for short expressions, everything just stays in registers the whole time. Frank, if you want to go to the next slide. Yep. So here's an actual bytecode routine that implements, in this case, the compare less than immediate float instruction that we saw above. At the top part here is the actual Go source for this, which is just a assembly routine with 2 macros in it. So it's not particularly revealing. But the way these work is that we have a predefined register convention for how each of these routines is entered and how the routine is expected to call the next routine subsequently. So the first thing that's happening in here, the first instruction here, is loading the immediate 3 and broadcasting it across all the lanes. Then it's doing a little bit mask shuffling to put conventionally we put the predicate in K1, and since we're dealing with 16 lanes, the predicate's a 16-bit mask. It's splitting it into 2 registers, K1 and K2, because when we're dealing with floating point numbers, we need to use 2 registers to fit 16 of them. So ZMM2 and ZMM3 contain 8 and 8 floating point values respectively. We do this comparison, which is the vcomp less than, let's see, ordered, quiet, packed double. That's how you would read that. And then we concatenate the result. So the results get stuck into the masks again. We concatenate those bits back into K1, and now you've got your result. And then all the subsequent instructions in this routine are just the setup for the next instruction. So what's happening here is that it's parsing a single byte value, or sorry, in this case, a 2-byte value from the instruction stream, and that always lives in RAX. And doing a table lookup to find the actual 64-bit absolute address of this instruction and branching into it. So this is a super short instruction for us. Like most bytecode instructions are an order of magnitude larger than this. But this one's short enough that it fits on a slide, so you can kind of explain what's going on. So the amortization of the dynamic dispatch that's happening here between instructions tends to be pretty good. It's a fraction of a percent of the runtime overhead. So that's all I have for VM stuff. I think it's probably a good time to pause for questions.
Got a question on the way you write your primitives, I guess, if you'd call them that, your bytecode instructions. You said that you write them all in assembly, and porting it to other architectures would obviously be a lot of work. Did you think about, before you started, stuff like C to Go ASM, which came from MinIO? I know some people on your team from MinIO. What did you think about, sort of writing it in C, using a C compiler to generate all your SIMD code from intrinsics, and then kind of generate the assembly or something like that, glue that to Go that way?
Yeah, there are a couple different angles there, so I'll try to address them each. And one issue I've had with intrinsics in the past is just that the actual quality of the code that's generated tends to be pretty poor. Like occasionally you'll run into issues where GCC will just generate totally garbage instruction sequences, despite coaxing it into. So then you have to start writing inline assembly, and it just turns into writing assembly all over again. The bigger issue is the register convention, writing these routines so that they actually comply with the pretty weird ABI that we have, like which registers are sort of callee save in this ABI, would be a real challenge. And then, yeah, I mean, there's a historical reason, which is simply that the VM started really small, and it grew and it grew and it grew, and now we have 15,000 lines of it. So early on, when it was really simple operations like this that comprised most of it, there really wasn't a lot of work to get it all set up. And now that we've invested a lot of time with a team of engineers extending it, it's quite a lot of code. So yeah, it'll be a challenge to port. I think we can do some of it mechanically if we have to, because the correspondence between instructions across the architectures is so close that I'm not sure. I think probably each function could be done maybe 80% mechanically and then 20% manually, and just go one by one and start implementing routines. But yeah, it'll be a pain when we do it.
Makes sense. The other thing I wanted to ask you, which I don't know if now is a good sort of point to ask that question, given I can sort of see where the slides are going on the screen there, but did you think about using a GPU for this? Is a GPU amenable to this, aside from the data load issue? Obviously, maybe an integrated GPU, which is becoming more and more popular now, looking at Apple's silicon kind of direction.
Yeah, I mean, I think it would be really awesome if we could do that. I think one of the things that's nice about one of the reasons we picked AVX-512 is that it's super powerful and available on commodity hardware, sort of. I mean, it's weird. It's no longer available on laptops, but I have a laptop that has AVX-512 on it. And you can get like all the C6 generation AWS instances have this available. So in terms of performance per dollar, particularly in the cloud where we're sort of stuck, right? Because we read data out of S3. If we're not in the same region as the S3 buckets that hold the data, all of the rest of this hard work doesn't even matter, right? So we're going to be paying AWS for these cycles. So we want to sort of tune for what's the best throughput per dollar we can get from AWS, and these like AVX-512 on C6i is really good. My guess is SVE on Graviton 3 is also good, but we'll have to have to do some work to get there.
Yeah, and also, I mean, the memory, obviously, we can use literally, almost terabytes of memory on bunches of servers, which, is obviously on GPU. VRAM is just very, very expensive, right? So
we can get the query engine on my Ice Lake workstation can chew through about 140 gigabytes a second. It'll hit RAM speed basically on the DRAM bus, which is more than I think you'd be able to get out of a single blade solution just over the PCI bus. So you'd sort of be stuck. Yeah, you'd have to use an iGPU, and even then, I think you'd still be memory bound. So at a certain point, we're most interested in like memory bandwidth and memory architecture. I think Sapphire Rapids is probably going to be a nice uplift for us for free when that becomes available, because there's just more memory bandwidth available.
Mm-hmm. I guess JSON is a pretty verbose format for the actual data that's probably being held. Have you thought about effectively having a pre-processing step, or you kind of stream it into a more compact format where the memory I/O then is not the bottleneck, and then
we already pre-process all the JSON into a format called ION, which is a binary format that does string and turning and all kinds of other tricks to make it smaller. Mm-hmm. So the footprint relative to the original JSON size is usually like 5x smaller, sometimes more, because we do some pretty aggressive string and turning. So that's also an important part of the performance story that we totally glossed over here. But there's a pre-processing step. So we reorganize. If you have JSON data in like 6 million S3 objects, we collect it into a much more reasonable number of objects. We build a secondary index on the timestamps. We do string and turning. We do compression. All kinds of stuff. So because otherwise you spend all your time reading data from S3, which also you don't want to do.
That's really nice.
Curious,
Okay.
Are you able to use the Go assembler just out of the box for this? I know some guy on GitHub has pulled it out of the compiler as a separate package. I'm wondering if you require any customization.
We haven't. I mean, there's been lots of like wailing and gnashing of teeth over the assembly syntax, because if you hire someone who knows AVX-512, they know Intel syntax or maybe GAS syntax, but almost certainly not Go syntax. So it's like, it's annoying, but it hasn't been a deal breaker. By the way, thank you for Avo. It was not something we use for this, but we use it elsewhere. So,
oh, cool.
Thanks for that.
Yeah. I'm just going to say I'm fully aware of the ways in which Go assembly syntax is odd. You mentioned you use a register allocator somewhere. I was curious. Do you ever find that 8 mask registers isn't enough?
So the predicates that are in the SSA, those always end up in K1 between instructions.
Okay.
And then the handwritten code, like 8s, you sort of run out sometimes. It's not too bad.
Okay, but because it's written by hand, you're not having to do some kind of like automated spilling or anything like that.
Right. Yeah.
Okay.
Yeah. That's another reason why tool assisted would be a little difficult is we don't really have scratch space available. It's allocated explicitly. So if it was tool generated and it had to spill, we'd have to like teach the tool how to spill it in the right way and stuff.
Cool. Thanks.
Mm-hmm. Okay. Thanks, Phil, for explaining all the low-level details. I have a couple more slides, kind of also at a higher level, and some performance data here, and even do the risky part, a little live demo. But like I said, I mean, we really think we're shine or strong at sort of huge quantities of JSON data, which fundamentally is obviously sort of schemaless. And we've been working with a couple of data sets, and one data set that we found to be pretty interesting is actually the GitHub archive data. So this is data that goes back to 2011. And GitHub has a total of 20 odd sort of events that they basically send out. There's actually a really nice project, the githubarchive.org, that has assembled all this this data. And also in there, yeah, fundamentally there's a payload sort of record or structure, and this payload will vary, you know, obviously per sort of event type, and some are relatively small, but some also can be really large. With you know, think of large, you know, sort of pull request or commit requests. So on average, every record is about 4,000 bytes, so pretty rich and detailed information. And yeah, up until essentially now, in total, it's close to 5 billion records. And if you look at the raw sort of uncompressed JSON size, it's actually somewhere like 16 terabyte of data. But as Phil was also yeah, mentioning before, we actually converted in a compressed binary version of JSON, and it's something called Ion, which is, you know, it's actually an Amazon sort of standard, which is also open source. So and this data lives in object storage. So for us, the GitHub archive data is something like 1,250 sort of blobs of objects, and spanning again compressed 1.6 terabyte of data. This is actually one of the JSON data sets where we see the least amount of compression. On other data, we can, well, here the ratio is about, say, you know, it's 10 actually, but that's again on the lower end. We see 20x or sometimes even 30x. But let me quickly switch screen and then show a quick live demo. So let me go to another window. That's going to be this window. So yeah, fundamentally, I can run a query here. So this is running against sort of our cloud solution. I'll talk to that in a second. But essentially, you know, this is just a REST API. What we do is we can send a query with, in this case, yeah, unfortunately URL escaped, but it's basically doing a count star across the whole data range going from 2011 to now. And you can see there's a count star, so it comes back with the 4.7 billion records. And there's a bit more detail here. So you can actually see that this query in this case took close to 12 or 13 seconds. We're actually running this across 2,000 cores. We're scanning about the Ion compressed on S3 is basically 1.6 terabyte of data, but if we decompress it, it's close to 12 terabyte of data. So that's kind of the Ion decompress that we process through. So we're processing close to a terabyte of Ion per second. And in terms of JSON, it's more like, say, 1.5 terabytes per JSON per second. But let me run a bit more interesting query. So now I'm doing basically sort of a distinct repo.name and doing a where clause where we basically do a case insensitive like on everything that basically contains friend Torvalds. So here you can see the response coming back, and again, it took basically 13 seconds, almost sort of the same throughput. And let me do one more query where basically we touch the payload.action for in this case the issues event. So yeah, that's obviously that's when you create an issue on GitHub for a public repository, you get that back, and yeah, we're doing basically a group by on the payload.action, and here the result comes back, and again took close to 13 seconds. In case that we are spanning or searching the full 12 years of GitHub archive data, yeah, we search through all the data. But if you specify a certain time range, then if you search through half the data, effectively, it will take us half the time. But fundamentally, yeah, right now we're processing close to, or we're querying close to half a gigabyte of sort of ion data per core per second, yeah, we'll probably can increase that a little bit more as we improve our code. But yeah, if you have, again, this is 16 terabyte of data. And let me go back to my presentation. And here is it. We're still kind of working on our benchmarking also against other sort of solutions out there, and also solutions that are essentially, consumption-based pricing. So in our vision, as part of our sort of cloud solution that we're working on, we really want to have, again, sort of a consumption-based model where you pay on the amount of data ultimately that you query through. And obviously, with querying large amounts of data, there's two factors that are important. You want it to be as quick as possible, and yeah, you want it to be as cheap as possible as well. And what is interesting is that this GitHub archive data is actually available as a public data set on BigQuery. And I must say BigQuery gives you pretty good performance, but it becomes really expensive at this scale. So basically the query that I just showed you, you can see our system, we can do it in say 12 or 13 seconds. You can do the same query on BigQuery. It's a little bit slower, but let's say it's fundamentally sort of in the same ballpark. But as you crunch through terabytes of data, BigQuery is basically $5 per terabyte. So yeah, if you go through 10 or 11 terabyte of data, a single query becomes $50 or more. And because we can run so much more efficiently with AVX-512, and again, basically for us, one core, we treat it as sort of having 16 sort of subcores. We think we can do a similar query in say $2 or something like that. The kind of this metric sort of gives an overall advantage that we have over not just BigQuery, but also other solutions like an S3 Select and an Athena, where you can see that an S3 Select is not that expensive, but rather than talking seconds, at this scale of data, again, going through say 16 terabyte of JSON, S3 starts to take 3 minutes or thereabouts. And obviously S3 Select is actually, it's basically, there's no aggregations that you can do. It's basically just a where part of basically a SQL statement that you can do. Obviously in AWS there's also Athena. Athena is $5 per terabyte, and basically full-fledged sort of SQL engine. So you can do all your group bys and orders and what have you. It's 2.5 times more expensive than S3 Select, and we found specifically for JSON data, it's about 3 to 4 times slower than S3 Select. Yeah, so we think we have a pretty compelling advantage over these other solutions. They're also sort of priced on or have a consumption-based pricing model, and with the data coming directly out of object storage, out of S3. Here is another slide showing some measurements that we've done across actually a different number of nodes, and this is actually measured at a terabyte per second sort of querying capability. So you can see at sort of 30 nodes, and here a node is basically an EC2 instance with I think 64 CPU. So basically sort of with the current performance, and I'll talk about the difference between what I mean by warm and cold in a second, we can sort of process a terabyte of JSON per second using give or take 2,000 cores. But as you scale up, we can hit basically 2 terabyte per second, almost with a linear, doubling the number of nodes. And we're showing 2 graphs here. Sort of the lower graph, that's what we call kind of our cold performance, meaning we do cache the sort of compressed IM data in DRAM. So obviously, if you just spin up a cluster, nothing is in DRAM, and for the GitHub archive data, we need to load the 1.6 terabyte of data into DRAM. You can see there's about a 2x difference in speed. So basically, for the same 2,000 cores, essentially it would take twice as long. So instead of say being 12 seconds, it would be 24 seconds to fetch the data from S3, and we basically cache the data that we load from S3 for a certain period of time in DRAM. So second time a query comes around, if it happens to be in DRAM, then you sort of get our warm performance, and that's as you can see, it's a fairly sort of linear scaling as you sort of add more horsepower essentially to your query performance. Let me go to the next slide. So essentially around our core technology, we've built a scalable sort of cloud architecture. So we can run queries distributed across a cluster of servers. We use basically a consistent hashing strategy, or if you have 10 servers, fundamentally, we chop, say, the 10 terabyte of data that you want to crunch through by 10, and each server gets a tenth of the data and does basically a tenth of the work. But fundamentally, our architecture is fully stateless. So our cloud is just a bunch of, compute cores, memory, and fast networking. There's no, local disk that we use, so no NVMe or SSD. We've actually found it's just as fast to load stuff out of object storage over 100 gigabit networking, provided that you use S3 tricks as sort of multiple range gets to get more throughput on a single object. So essentially our cloud solution is going to be serverless. It's also going to be obviously multi-tenant and fundamentally pay as you go. So the more work you ask it to do, obviously the more you scan, the more you pay. Flip side is if you don't do any or reduce your query rate, yeah, you're going to be paying sort of less. And maybe also of note is something that we've done quite a bit of testing against this sort of elastic search, which quite a few people use for JSON data. So we actually, if you ever worked with Elasticsearch, you might know Elastic has its own sort of query language, which is called the Elastic DSL. Which is fundamentally sort of a JSON, definitely not SQL, not even well, maybe you could call it NoSQL, but it has its own sort of query language, and we've sort of written a proxy to kind of translate the Elastic DSL into basically our SQL or particle flavor of that, being able to also use the JQ style path naming for basically schemaless JSON data. And yeah, a couple of the use cases so far that we've seen where one thing that we've noticed is that a lot of people are already aggregating tons and tons of data as JSON into S3, and there you can talk about the cloud trail data and IoT sensor data, networking flow logs, various types of DevOps and AIOps and all that stuff. And especially I think when you talk about scale, so Elastic, as it sort of scales up, really starts to struggle with terabytes and terabytes of data, and also if you use local NVMe, you're going to limit the amount of data fundamentally that you can process. And we see a lot of people kind of more thinking in terms of days and weeks of retention, whereas we say with object storage you can start to think of months or even years of retention, because S3 is so cheap that you don't really have to throw data away. And kind of with our architecture, even if you want to drill down and say a month of data which is a year old, if it's still in S3, we can load that month, which is sort of a year ago, into DRAM and basically give you terabyte per second query speed on that data, just as if it's been generated yesterday. But yeah, this sort of brings me to my last slide. So anybody have any questions, and we'd be happy to address those. But also the core of our product, which includes all the AVX-512 code and actually the whole VM and SQL parser and SSA, everything is open source. So if you enjoyed the presentation, we'd appreciate it if you would be willing to give us a star on GitHub. And also we are sort of testing our Sneller Cloud solution. So if anybody's interested in doing some testing with it as a design partner or sort of a beta customer, and you have a couple of terabytes of JSON data in object storage, we'd be happy to talk as well. Or maybe if you know somebody who's sort of struggling with this problem. And here this is both Phil's and my email address as well. So that's pretty much all I had. So any questions on what we've been talking about?
So much, guys. That was great. Anybody have any questions for either Phil or Frank?
I've got a quick one. Thanks for going through all that. That was really interesting. It's maybe not related to the product or the tech or even just why you use Go, but why did you pick AGPL as your license? I understand that it's typically used for network services, but any other reasons?
Well, the primary reason is that, well, we might be flattered if Amazon were to offer a managed Sneller. Commercially speaking, that wouldn't be the best thing. So we considered going, AG or Apache 2 and then switching. I mean, some actually previous company I worked at, Minio, started as Apache 2 and later switched to AGPL. In our view, AGPL is kind of the purest form in open source, because you can use it as long as your product is also open source. So Amazon is happy to use it and even offer a managed Sneller as long as they open source everything, which might be a little challenge to those guys. So that's why we opted for AGPL.
Okay, good to know. Thank you.
I'm curious about your progress on ARM, specifically because, to my knowledge, the Go assembler has pretty poor support for the modern instruction sets. Are you having to write your own assembler for that, or are you? Yeah, I mean, maybe you can talk about it.
Yeah, I think you can stick in bytecode, which is ugly, which is one way of achieving. But to be honest, we haven't, so far we focused on AVX-512. Actually, we focused on AWS. We're gonna be, we're actually looking at Google Cloud as well, and even Azure with Azure Blob shouldn't be too much of a lift to support as well. So obviously, AVX-512 is readily available even in hybrid clouds and private clouds and what have you. And thus far, obviously, there's Graviton 3, and I think Graviton 3. It would be interesting to see what kind of performance it gives. Obviously, SVE2 is 256 bits, so it's basically 8 lanes, not 16 lanes. So yeah, I think we would like to look at it, but so far, we focused on Intel. I think, well, not eventually. At some point in time, we'll put in the effort, but it's not a near-term priority at this point in time. I would say.
I think if we had to do it right now, we'd probably write it in, gas syntax or Intel, in gas syntax, and then just take the binary output and basically reassemble or disassemble it, reassemble it.
Yeah, fair enough. There is a CL out. It has been for a long time from ARM, but didn't make it into Go 119. So I think it's going to be Go 120, and then we'll just have support in the Go assembler. So.
Yeah, that would be ideal. Not that necessarily I want to learn a third syntax for SVE or whatever, but
yeah. Are you at all concerned about Intel's long-term commitment to AVX-512? I'm referring to the fact that their architectures with the efficiency cores don't support it, or they turned it off.
In our conversations with them, they seem very excited that someone's using it.
Right, but being the only customer for something doesn't necessarily feel that secure.
Yeah. I can only guess. I am not super worried about it. I think to remove it from the server line of products would be a big deal, I think. Because the reality is there are workloads that use it now. There are very few workloads that depend on it like we do, but it's there. And actually, on Ice Lake, it does actually go faster, unlike in previous generations where the speed up is often negative.
Yeah.
You know,
Uh,
so I think the fact that it goes faster is probably sufficient to keep it alive, and we no longer
yeah,
we're not dying for any like additional extensions to it. So even if they just keep it on life support, we'd be happy.
Right.
Yeah.
And it's probably a long-term concern. It's not like they're going to disappear next year or anything. Yeah.
Right.
correct. And again, I think actually I'm happy that ARM also has SVE too, right? Because again, fundamentally, it's the same thing, right?
And
so
the RISC-V
is it even
Vector Extension is
RISC-V?
also
Yeah.
the same
Yeah.
kind of architecture. They only have one predicate register for whatever reason, which is a little annoying, but that's also another target. So I'm at least optimistic that long term the design is portable, and you know, fingers crossed, we don't have to deprecate anything in the future.
I'm curious about your testing, because you've described an extremely complex system here. Like, do you use fuzzing? I mean, what's your approach? You know.
Yep. Well, it's a lot of different pieces. A lot of them get fuzzed. For the VM, we have a test harness that has several hundred and counting. Basically, you can hand type a query, a data set, you know, input, output, and there's a lot of those. For some opcodes, you can just test exhaustively, so it's not that hard. The VM is actually one of the more easily testable things because the behavior is deterministic. You're not worried about like, oh, if I scale up to 100 nodes, then this weird thing happens. So that part of it actually has not been a major source. You'd think it would be a major source of problems, but it actually, as far as like weird headaches that have had to go fix at odd hours, the VM is not the primary source of that. The query planner is pretty complicated because it plans a multi-machine query across a bunch of weird constrained operators. And yeah, I mean, essentially the test strategy is we have a lot of different packages that implement the different, you know, parts of the product: the query planner, parser, the VM, the ingest pipeline, serialization, all that stuff, and all of it that's publicly facing is fuzz tested. We do, one of the reasons we do the ingest, the pre-processing ourselves, as opposed to having other people do it, is that we can guarantee the bytes that go into the engine are bytes that we created. So when we're fetching the data, we insist the e-tag of the object matches and things like that. So we don't have to worry as much about totally crazy stuff ending up in the VM. We've seen the data before. We have some idea of what it looks like. Yeah.
And also, actually, you know, basically all the opcodes are fundamentally branchless, right? So, I mean,
it's easy
like
to get 100% test coverage. Yeah.
Exactly.
Yeah, that's nice. Yeah.
So.
I have a question. It seems to me for the query, the I/O will be a kind of big bottleneck rather than CPU when you're kind of fetching data from the network. I mean, do you have some examples using Snedler versus just a direct CPU to compute data from S3?
Yeah. So the warm versus cold example that Frank pulled up here, the warm is data out of DRAM, and cold would be out of S3. So there's basically a 2x performance hit coming out of S3. We compress the data, which means that if we're pulling, let's say, 50 gigabit from S3, which is the most you can get on a C6 instance, you're getting more than 500 gigabit, so like 60 gigabytes a second of decompression output. So it's still pretty decent, even when you have to go to S3, because we use data compression. If we didn't, it would be, it would be awful.
Yeah.
But yeah, it costs about a factor of 2, and we have a DRAM cache on the machines for data segment. We call them segments that have been accessed recently. So we basically break the data up into pieces, and those get hashed onto machines. The machines store them locally and evict them when they get old. And if you hit the same piece of data more than once, you'll often be getting it out of DRAM, and so the performance is is pretty good there.
I see, got it.
Any other
By the way,
questions?
sorry, I suppose there must be some GPU-based solutions for CMIT, right? I'm not sure. I don't know this piece of this area.
Yeah. Our product guy is actually from OmniSci, which does a GPU, GPGPU database kind of thing. And I think there are other products out there as well. Which, yeah, those are crazy fast. The biggest problem is they're constrained in weird ways, like the size of the working set, or like if you're doing something really computation intensive, they're great. But oftentimes you're doing something that's really lightweight in computation and just really expensive in total throughput. And in that case, your DRAM is actually potentially faster than your PCI bus. So if you just have to trade one or the other, you're just going to pick DRAM because it's there. But yeah, it's an area I'm less familiar with. I think, as I said earlier, I think an advantage we have is just that we can target a commodity hardware, cheap stuff.
Cool.
Okay, any more questions, or we've gone a little bit over time, I think, but hopefully that's okay.
No, it's not. No, I'm just teasing. No, it was a great talk. Everyone, I love the engagement, and obviously sparked a lot of interest for sure. And if you guys want to drop your contact information in the chat in case people would like to contact you afterwards for follow-up, that would be great. I want to thank you both for coming out, and we really appreciate it. So thanks, guys. Very, very appreciated. See, they made it. So if you want to submit a talk for next month, we would love to hear from those who are here tonight. So I'm going to go ahead and stop the recording. And